Today we will be focusing mostly on nanomechanical properties that we can check using AFM. On this slide, you can see different AFM measures of mechanical properties of a surface that we can record by interaction force with respect of tip surface distance, or by measuring effect of the interaction force on some parameters of the tip's oscillation. So initially, the methods were classified according to the AFM mode that was used to generate a topographic image, like off resonance or on resonance. So this classification scheme is useful, but a bit incomplete because it does not inform on how mechanical properties are obtained. So the total summary is represented in the middle picture. So the methods, all the methods can be classified according to different features, such as the quantitative character of the type of observable, or a ratio between the resonant frequency or the modulation frequency. The most distinctive classification comes from how values of mechanical properties are obtained. So our first distance curves methods record a force distance curve on each point of the surface. So you can see this on the left-hand side. In parametric methods, some observables such as the amplitude, the phase, or the frequency, frequency shifts, they are recorded on each point of the surface. So this is the right-hand side picture. So you see the difference, right? And the analytical theory transforms those observables into terms of parameters of the interaction force. So let's just talk about what is surface and what is interface. Surface is the boundary between gas and solid, or vapor and liquid, or liquid and solid. Interface is the boundary between two solids or two liquids. So basically what happens in the fundamental physics, that the atoms that are at the surface are undergoing compression or tension simply because they don't have adjacent atoms next to them that will keep them in their official lattice size when they are surrounded by bulk atoms. So that idea raises this concept of excess surface energy that is created, and it happens to result every time when you create a surface of any nature. So the question then becomes is, how do you characterize this excess of surface energy? So this problem was well addressed long time ago, and we all know a scientist Jung, and then he kind of created a theory back in the beginning of the 19th century. So he realized that if you just calculate the work, that the work here is dW. So he realized that if you calculate the work that is required to produce a surface or an interface, this work is proportional to the surface area, and that's been produced in the process of splitting a solid or a liquid. So what we then say is that the amount of work required to generate a surface with the area dA is proportional to, so these two variables are proportional to one another. And here we introduce some constant gamma, which is referred as a specific surface energy of the system. And so gamma is a scalar quantity. It's not a vector. And this is just a number and has units of energy per unit area. So typically it has units of joules per meter squared or millijoules per meter square, depending on which textbook you're reading. And this parameter gamma is like a restoring force that resists the increase of the area, and it is equal to the surface tension if you're dealing with the liquid surface interfaces. This is basically what Jung suggested. So for liquids, this gamma is, again, it is equal to surface tension, and it becomes a vector in liquids. And it has units of force per unit length, so it's usually nanometers per meter. And surface tension acts, so it decreases the surface energy of the system and leads to some well-known effects like liquid droplets forming spheres or meniscus formation in a small capillaries. If I just come back for a second for the previous slide, again, surface energies can be measured in a variety of different ways. So the standard way is to do is like your material has a liquid phase in it, or you can put a drop on a surface to measure contact angles. So here you can see again all these methods that can be used to measure this. Just keep these methods in mind when you talk about surfaces and interfaces. And for example, for low energy solids like polymers, we usually use contact angle measurements. It depends on the surface roughness. If we want to use to measure like mechanical deflection, then the temperature should be varied, and we might use metallic cantilevers. So in generally, we have like three terms that we're looking at: is surface energy, cohesion, and melting temperatures. I will talk about cohesion a bit later. So all these terms are related to each other. So high surface energy produces strong cohesion, and usually these materials have high melting temperatures as well. Okay, so if we go further, let's talk about adhesion between different surfaces. So again, high surface energies refer to strong cohesion and high building temperatures. So why do different materials stick to one another? You usually want to minimize that sticking in atomic force microscopy applications, and here's like the list of different reasons why that could happen, why a tip in airfam could stick to a substrate based on its surface. So it can be a mechanical adhesion between the tip and the substrate. It could be a chemical adhesion where there are chemical bonds formed between atoms and molecules on the tip, with the atoms and the molecules on the surface. Another example is dispersive adhesion. This adhesion is based on the van der Waals interaction between atoms and molecules in the tip and atoms and molecules on a substrate. And if the tip or the substrate tends to be charged, you can get electrostatic adhesion. And lastly, if your tip or substrate is made up of polymer-like molecules, it is possible that those polymer-like molecules could be entangled to produce a diffusion contribution to adhesion, and will be called diffusive adhesion. Of course, not all of these mechanisms apply to a typical atomic force microscopy experiment. I would say usually that is possible that chemical adhesion and dispersive adhesion mechanisms are like possibly the most important in the AFM measurements, but in principle, all 5 of these different mechanisms could be like input something in your measurements. It is also follows from the fact that the total surface energy between 2 materials could contain contributions from each other of the 5 different mechanisms. So, for example, you can have dispersive contributions in the surface energy. You can also have a column contribution if there's happen to have ions that attract one another across the interface, and so on and so forth. So this is just again the list of these adhesions. So you have this in front of you. So just again, adhesion is determined by the molecular force of attraction between unlike materials. Cohesion if you have 2 similar materials. And the adhesion that results when material like 1 comes into contact with material 2 is basically related to the force of attraction between the unlike material, between the unlike molecules of these 2 materials. So if you have a tip coming into contact with the surface, if the material in the tip is different than the material on your surface, you can either get a high adhesion or low adhesion. It will depend on what the molecular force of attraction between the atoms and molecules you have across the interface. For example, if you get low adhesion, you tend to say that's characterized by low surface energy. So this process is illustrated here. As an example, I just brought like a drop of liquid on the surface. So if the drop adheres very tightly to the surface, we refer to that as high adhesion. And basically what's happening is the molecules in the drop are very strongly attracted to the molecules in the surface. As the adhesion decreases, you end up with a situation where the molecules in the droplet are more strongly attracted to each other than they are attracted to the atoms of the surface. So here you can see these arrows in the drop. So that produces low adhesion, and this is the example that illustrates like on this on the right hand side. So the same thing happens when a solid like tip comes into the contact with the substrate. This adhesion can be high or low depending on how these atoms are interacting with one with another. So let's just bring a bit more formulas to these terminologies. And here we have cohesion and adhesion. So these are 2 quantities we were talking about. So cohesion is here, as again, is like the interaction between 2 similar surfaces or materials, and adhesion is the interaction between 2 different materials. So for 2 different solids, the case of most interest in atomic force microscopy, of course, right, is when 2 materials come into contact with to one to another, and So here I just illustrate as a two cubes. So when material 1 is in the close contact with the material 2, there will be an interfacial energy, and this will be referred as gamma 1 and gamma 2 for each material, especially when they're separated from one another. And surface energy of material 1 is referred as like gamma 1 and gamma 2, right? So here you can see how these interaction is calculated. So you have the gamma 1 and gamma 2 from each material as a contribution minus this energy, interfacial energy, when these two materials are very close to each other and contacting. So that's why we have minus here. And the contact area between these two materials is represented by this parameter dA, and this is how the interfacial energy is calculated. And this we have the work of adhesion per unit area. So we have one question then: how to determine this gamma 1, 2? Because gamma 1 and gamma 2 comes from the characterization of each material, but we don't know anything about gamma 1, 2 here. So the answer to this question is in the Lifshitz theory for the interaction potential energy. So for the next few slides, I will be talking about tip surface interaction, and I will talk about Lifshitz theory, just explaining where all these values are coming from. So first of all, I will start with the quite simple example. So the problem is that we worked out interaction energies between two molecules, separated by some distance z. We were talking about this like last lecture and on the first lecture with all these column forces and so on. Now we have to interpolate this knowledge over the shape of the tip and the shape of the sample to get the potential energy of tip surface interaction. First of all, and we will replace the tip with the sphere just to have like a model, the mathematical model. And also I just want to remind you that the interaction potential energy depends on the constant C of van der Waals, and it's proportional to 1 over the 6th power of the separation between the atoms and the molecules. And the minus sign indicates that interaction potential energy is negative, and it shows us the attractive interaction between atoms or molecules that undergo these van der Waals force. So this, you should remember this equation. So to start, I would like us to think about the simplest case you can imagine as one atom or one molecule interacting with a flat plane. So a flat plane here is shown as this green rectangular, and just to understand what is happening here. So these two images are basically showing the same thing, but from different angle. So for example, on the left-hand side, what you can see here is the same if you look at this image, but from a bit from the right side. So this is the same thing, but view from the different angle. So what we are going to do, we will start to transition to a set of coordinates or set of variables that make sense specifically for atomic force microscopy. And we will say that an atom or a molecule is located the distance d above of a flat plane, and we have infinite extent to it. So we have distance d, and then we also have z called 0. It's infinite extent. And we're also going to assume that the interaction potential between the atom outside the plane and any particular atom inside the plane is basically covered by this 1 over z of the 6 of van der Waals interaction potential energy. Then the interaction potential energy is the sum of all pairwise molecular interactions. So this means that 3, 4, or 5 or 105 body interactions are not included. Only we are talking about interaction between one atom with another atom. And so we are going to have, so we will separate this plane into rings. So this is the ring that belongs to a plane, right? And we will calculate the potential energy that molecule and entire plane has. So this plane, again, we are splitting into symmetrical rings. So this red thing is the ring from the right-hand side point of view. And the dark red square is basically the thickness of this ring. The ring will have the radius x, and the thickness will be dx, and the width, so the width will be decided as d zeta. And we will going to allow the radius of the ring to vary, as we allow also the separation of this plane of the ring from a point 0 where we have our molecule. And again, we will neglect interactions between the molecule and all atoms in this full plane. We will just consider, so let's say here, black point is one atom that belongs to this plane, and we will calculate the interaction between this atom and nothing else. So this interaction is going to depend on the number of atoms in that ring, and the number of atoms in that ring is going to depend to the number density of atoms or molecules in the substrate. So this is number of density is depicted as ρ1 here. So basically it is not the mass density, it is the how many atoms per cubic meter or nanometer you have in this ring. So this equation on the right-hand side says that when you integrate this van der Waals interaction potential over all atoms or molecules in the substrate, you will end up with an expression for the interaction potential energy that varies as 1 over distance cube that the atom or molecule is positioned above the substrate. So this is the first step in the process of understanding how tip interacts with the substrate. So next step is to integrate the atom plane van der Waals interaction over the volume of a spherical AFM tip. So what we did before, we just chose a point on the tip, and we were considering the interaction between this point and the plane. Now we are going to calculate the interaction between the whole volume of the tip with the plane. So this is the plane, this is ρ1 is the same thing as here. And we would say that the tip has the density of ρ2. We are going to use the sphere to approximate the tip. To do that, we will take the result we just obtained, 1 over d cube dependence, and now it becomes d plus zeta cubed, because zeta is here and is going to tell where the particular atom or molecule is located inside the tip. So zeta is here, and now we have basically two distances to think about. And I mean, I didn't put here all the calculations, so this is the final equation. So basically, here we have the radius of the tape divided by 6d, and it says that interaction potential energy between a sphere and a substrate, if the apex of the sphere is located at the distance, so this is apex of the sphere, is located at the distance d above the substrate. So the potential energy varies as a constant h. So the constant h here is the simplification of this equation. And this constant depends on the number density of the atoms in the tip is ρ2, and in the substrate is ρ1, and depends on the van der Waals coefficient C that we discussed already, and it also depends on the radius of the tip and inversely proportional to the separation, so the distance d between the tip and a substrate. So this constant h is the Hamaker constant. So usually in the literature you can find various symbols used for Hamaker constant. Some people represent it just capital H. You will also find articles that are represented by capital A or capital A with sub H. So they are all referred to the same constant, just different abbreviations. So again, so the constant is this constant is the product of the number of densities times the van der Waals constant, and it describes how the two atoms interact one with respect to another. So here we approximated tip as a smooth sphere, and this is again is a fair question whether you can do that calculation using this model, right? Because it's quite an approximation. And here we are coming to Lifshitz theory, because Lifshitz actually thought about this approximation and he tried to calculate this constant. Okay, so Lifshitz theory was developed by a Russian physicist in the early 1960s. And I would not put all the derivations here, just this is the final equation that he got for a Hamaker constant. So the final result is that, again, so this Hamaker constant is a functional dependence on distance d. And as you can see, the expression is a bit more complicated, right? So to calculate this constant in precise way, you must integrate over frequency dependence of a quite lengthy expression here that contains complex dielectric function of the interacting substances, which means FM, tips, sample, and also the medium. So for example, you can calculate this interaction between tip and sample inside the liquid. So liquid here, it will be immersion medium. So these frequency dependent fluctuations include not only electronic displacement with the neutral atom, but also different mobile electrons in metals and ions in the solution, and also takes into account these different vibrating of rotation of different dipoles and media and so on. Of course, you should, I mean, I do not expect you to remember this particular equation, but it is good to understand that this expression also makes two predictions regarding attraction versus repulsion. So if we have identical materials for the tip and the sample, then Hamaker constant is always positive and the interaction is always attractive. If you have different tip and sample materials, then in this case, the interaction can be attractive or repulsive, depending on the medium when we have around tip and the sample. And if we're talking about the vacuum, then the interaction will be always attractive, and it does not depend on the composition of the tip and the sample. So why is this important, right? Why? And why is it interesting? Because within the context of AFM, every time when tip comes to a contact with a substrate, you are actually forming an interface between material that comprises the tip and the material that comprises the substrate. So there are many ways to describe the interface, and so one of the approaches I just was talking about, and that's why I showed you Hamaker constants and we were calculating different surface energies. What are the typical values of Hamaker constant? So to estimate this, you have to know properties of the materials of the tip and the sample, and different values actually scattered around the literature, so you can find a bit different values. But if you calculate it, like if you calculate all of this and this, then the value is about 10 power minus 19 or 10 power minus 20 joules. So this is like, this range is about like most widespread for material systems. So so for the most solids, you can think about Hamaker constant as this big. What happens during the contact? So again, you should understand that the size of the contact is in nanometers, right? So we either have to pretend that the tip is made of atoms, or we have to approximate the tip as a flat surface or a slab. So it will be interaction between perfectly round tip and perfectly flat surface. So this is so-called bulk approach. This is atomic approach. The first choice when you pretend that the tip is made up of atoms and the substrate is also made up of individual atoms, it's kind of correct, but then you have to calculate the interaction forces between the tip atoms and the substrate atoms using like a lot of formulas that we're talking about in the very first lecture. The trouble is, of course, that you'll know that the chemical composition of the tip or the substrate, especially an atom by atom basis, is very complex, and we don't always know what kind of material it is, and you cannot calculate it every time for every single tip. It will be a lot of calculations and a lot of work. So on another hand, you have you can treat tip and a substrate relying on the bulk approximations. And then just what you should know is just the radius of the tip, basically, right? The problem with this bulk approach is that, of course, you're going to neglect atomic corrugations that exist on the tip. You're going to neglect the atomic steps, the atomic scale features. AFM, in general, as a method, it kind of jumps back and forth between these two different points of view, and just keep it in mind that depending on what you want to see or want to calculate, you might use different approaches here. Whether rigid tip or sample or soft tip and sample is interacting, the question is of how after here we will stop thinking about the tip as an atom-atom interaction, and I will talk about the bulk approach. So here is a Young's modulus, and the question is how contact force or contact energy increases as a function of tip displacement into the sample. And to begin with, I'd like to say that there are basically three types of external forces that in the form of solids. The first force is the force that applied to normal cube of material. We assume that this cube has cross-sectional area A, and we apply normal force as indicated here. So this is normal force, right? There are other deformations that can be applied. So for example, tangential stress or hydrostatic pressure, but these two deformations are not terribly interesting for AFM. So we will focus on the normal stress that is perpendicular to the plane of this cube. So the dimensions of the cube are L by L by L. And the question is the elongation of the cube in the direction of the applied force. So this elongation or the deformation will be referred as dl, and we can calculate this ratio basically of the stress to the strains. So the stress is defined as a normal force divided by a cross-sectional area, and the strain is defined as the change of the length, so dl by l, change of the length divided by the original length, L. So the ratio of these two quantities is just equal to something called Young's modulus of the material, and Young's modulus or elasticity modulus is often referred as a number, and it basically describes the resulting strain that is induced when a particular stress applied. The units of Young's modulus are force per unit area. And forces are measured in newtons, areas are measured in square meters. So the modulus will be newtons per square meter. And it is equivalent to Pascal. So 1 Pascal is equal to 1 Newton per 1 square meter in this cross-sectional area. It is also useful to have in your mind that a microscopic model of a Young's modulus. It is shown here. So we will think of a solid as a bunch of atoms that are interconnected by one by another with springs. So the spring constant in this particular case can be designed by a parameter K with a subtract atom to atom. What we like to able to do is to relate the effect of the spring constant and the measure and then the measure bulk cube of this material. So we can define how force is applied to each atom in the solid. And briefly, I will not put all the calculation. It looks like this. And the ratio of the stress and the strain can be identified as the Young modulus E in this case, E capital. And as a result, the effect of the string constant between atoms is equal of this E times the inner atomic equilibrium, so-called this one, the spacing between atoms. So the parameter that you measured in the bulk, E, has to be related back to this inner atomic spring constants. So just keep this in mind when you do the stress calculation. Okay, so it is also useful to try to relate these bulk properties that were measured back to microscopic properties. So here we'll treat the tip and cantilever system as equivalent point mass M, here, point mass M attached to a spring with stiffness K0. And then we have these simple harmonic oscillators swinging towards and away from the sample. And these resonance frequencies shown here. Of course, please understand that this distance is in nanometers, so it's not the scalable picture here. As one case of interest, we can imagine the tip exploring the distances between only attractive forces and that are felt in a certain distance. And basically what we are calculating here is the cantilever restoring force like F. and tip sample interaction force F between tip and sample. So these are two different curves. So the light gray curve here is the tip sample in tip sample interaction here, tip sample interaction, and the force that is developed by the cantilever is this line, diagonal one. And this brings us to adhesion maps. So in general, AFM enables like a new class of experiments. Here, let's first look on the top right. I think it's important to emphasize that once AFM gives these amazing images in 3 dimensions in a nanometer resolution, it also becomes clear that you can use AFM to perform an entirely new class of experiments. The idea is pretty simple because since AFM is a proximal probe, it just looks like so it attaches to the surface very locally. And you can imagine that if you're doing the image scan and measuring the topography of the substrate, you can see some nanoscale object that is on the surface. You want to learn more about that nanoscale object, what it is. And AFM allows you the possibility of asking the questions, what could be the structural properties of this particular object. So you might imagine being able to position a tip above that particular object and executing force versus displacement curve. And then then you can interpret this force versus displacement to some structural properties of nanoscale object of interest. So this is what a lot of people use AFM for. So now please look at the bottom graph. This is force versus displacement graph. So here we have a full workforce snapshot. And what is actually happening is so we need to look at the different points along the experiment. So the dashed line indicates what you would expect if the substrate were infinitely hard. So this will be just a horizontal dashed line. The experimental data always will lie to the far side of what the dashed line is indicating here. So, and look at this drop here. It actually shows that the tip is deforming in the real life. So you see the jump of the contact fixture here. And we already discussed in some detail of this this thing. And after the withdrawal, you see that the force versus curve displacement curve that please look at this area. So this force versus displacement curve, it allows you to map the adhesion of the tip to the sample. And this is what you see in your software during the experiment. So usually in the ideal conditions, like if everything is infinitely hard, this curve should go a bit higher up. But in a real life experiment, you might see the difference between these angles. So on the top graph, you can see force versus time. So this is the real experiment, like the actual what you see in actual experiment, because real experiment is done in the real time, right? So it's not like this is what you actually see in the software. So here, the top region of this panel. So here you can see what actually goes with time, and again, you have this a bit different angle between the theoretical calculations and the deformation, like in the real experiment when the tip deforms, and then after withdrawal, you have these a small overshoot that represents adhesion over time. So basically, these two graphs, they show you the same thing, but this one is kind of unfolded in a force versus time. On the y-axis, this is the loading force in nanonewtons. So each feature in that force versus displacement curve it can be mapped into a three-dimensional map. And so this gives you information about the sample. So if we come back to these schematics again, so for the instance, the loading force or can be indicated as a dot somewhere on the sample. And this point gives you the displacement of the substrate that's required to achieve by this loading force. And then we have this position INJ that you can use for further calculations and from the this force versus displacement curve that you can get after running the AFM experiment. So you can imagine making a modulus map simultaneously with a topographic map, and then also by measuring this lift-off force when the tip is at a particular point on the substrate. So all you have to do is to achieve this goal is to write some software that is sufficiently flexible and that allows you to pull off the standard force versus displacement curve, this curve, and then you can get the relevant information from this curve. So typically when you do an adhesion map or a modulus map, you do not perform it at the same resolution as the topographic map because of the time required to do this. So typically, if you had to make an estimate of adhesion map or modulus map, you will go for run about 128 by 128 pixels, and the image can be acquired in this kind of resolution in 5 to 10 minutes. So this estimation, it immediately tells you during your AFM experiment if you have a stable situation and you have a lot, or you have a lot of thermal drift when the adhesion is not good, and then it might show you what kind of things you have to do with your system to adjust. So these curves are very useful to just to check how your tip is interacting with the substrate, and you can get a lot of information out of that. So just an example. So on the left-hand side, you can see AFM topography and different multiparametric maps on the membrane that is absorbed onto mica and then imaged in the buffer solution. So here you can see these curves that I was talking about in the previous slide, and this is how they look in the actual experiment. So let's talk about this picture in a bit more details. So here you can see the recording of functionalized atomic force microscope tips. So here the functional, so you have some chemical modification or biological modification here. So on this graph, you can see, so this first curve and the second curve. So first curve shows you recording of non-specific adhesion, and the second curve shows you a specific adhesion on the tip that is carrying a functionalized peptide linker. So this is how you can actually check that you have something on your tip or not, because there will be a shift between non-specific interaction and specific interaction. So upon withdrawal, the linker is stretched, and the bond that is formed between the chemical group on the tip and the biological sample is kind of very stressed until it's being ruptured, basically. So the rupture force peak, this one, occurs at the distance corresponding to the length of the linker, L. So that's what this shift tells you. Here on the panel C, again, where the tip can be used to detect specific and non-specific interactions on a cellular membrane. So again, just number one here is non-specific interaction between the tip and the membrane, and this is the specific interaction using the linker. So basically, this is the drawing of schematics of what is happening in these graphs. So this is the length L, and this is the difference between these peaks that I was explaining to you previously. Here, you can see the distribution of the rupture forces. So each red curve is this rupture or unbinding forces on these molecular bonds, and this distribution depends on the loading rate. So, and then the last graph that I want to discuss is these basically probing forces breaking a bond, it allows you to determine parameters describing free energy barrier that stabilizes the bond. So these parameters include free energy difference delta G between the. So this delta G shows like the energy between bound state and transitional state. Transitional state is shown as this this symbol over here. And what else? You can also calculate the distance. This one XU. This is the distance separating the bound form of the transitional state, and also you can calculate the rates of bound state crossing the energy barrier in the absence or presence of any external applied force. So this is just an illustration how many details you can get out of these curves, and it is very particularly useful for investigation of different properties of the cell membrane. So another question is that is actually arises as especially when we're working with the cells, how we are going to do all these calculations that I was talking about, and how we're going to measure the elastic modulus, Young's modulus. So there are different models of the cells. So I just brought an example of two of the most widespread models. And let's start with the Hertz model. So here, the cell has radius R1, and it is located on the rigid flat substrate. And we have our tip with the radius R2. So the Hertz model and different modification of this model has been quite widely used to determine these elastic modulus of the cells. So in this model, the cell is assumed to be a homogeneous material, and the cell border is considered to be a well-defined interface. So this homogeneity of the cell material may be considered as a reasonable approximation for small deformation. So here this D shows the deformation of the cell surface. But this kind of approach is a bit too simple if the deformation is large. So another type of model has been developed. It's on the right-hand side. And this is so-called brush model. So the brush model also looks at the presence of different proteins on the surface of the cell. And just a bit of what is Z, Z0, D here. So Z is the relative position of the cantilever. So it is varying like on this axis. D here, this one, is the cantilever deflection. So you can see the solid line and the dashed line for the cantilever. So position Z0 is the non-deformed position of the sample. And the E here is the deformation of the sample. Z that is equal to 0 is the maximum deflection that can be assigned by a researcher. And the H here is the separation between the sample and the airflow probe. So this kind of model allows deriving like this elastic modulus of the cell body using extra parameters of the surrounding brush. And the thing is that when you use this kind of model, it gives you a bit different modulus. So for example, when you use Hertz module, the average Young's modulus of the cells is about 0.4 kilopascal. At the same time, the values derived from the brush model is about 2 to 3 times larger than in this model. So it is a bit hard to compare them, but again, it depends what kind of question you are asking. So Hertz model is a good model if you don't have big deformation of a cell membrane, but if you need to calculate like big forces, it is better to use brush model because it also takes into account these proteins here and their elasticity as well. Okay, and this brings us to lateral force microscopy. So this type of microscopy is particularly useful for identifying and mapping heterogeneities in the surface of with different characteristics. And it has like numerous different applications. And so here on the top level of this slide is a schematic illustration of the laser position. These pictures should be familiar to you already. And mechanism of lateral force microscopy is very similar to that of a contact mode. So in contact mode, the deflection of the cantilever in the vertical direction is measured and utilized to generate the surface topography, right? However, in the LFM, lateral force microscopy, the deflection of the cantilever is being measured in the horizontal direction. So we have horizontal component and vertical component. So the factors that determine the magnitude of this deflection will include the frictional coefficient, the topography of the sample, and also the direction of cantilever movement. And here on the bottom, you can see another like schematic illustration of the movement of the probe. So here you can see that depending on the surface structure, the tip can change its position while it is being moved along this surface. So this is just a reminder about these deflection points here. And yes, so this operation of lateral force microscopy and this cantilever movement is just like very important to just remember that in this case, the cantilever moves not only up and down, but also along its axis here. And so this is just like a simple approach, and then we can use this approach for force modulation microscopy. So force modulation microscopy is also based on the contact mode AFM, but it also has additional mechanical modulation that is applied to the cantilever during these contact scan. So the mechanical modulation of the AFM cantilever leads to an oscillation of temporal sample force, and it helps us to characterize the sample's non-mechanical properties based on the amplitude here and the phase shift over here. I will talk about phase shift a bit later. So the amplitude and a phase are sensitive to changes in the local elasticity. That's why I've been talking about Young's models for such a long time. And also it is sensitive for adhesion force between the tip and the sample surface. So this type of microscopy allows you to measure simultaneously some local non-mechanical properties, and also allows you to differentiate the material components in a qualitative way. For example, you have some polymer blends here, and then like as a soft region, and you can see these in the signal. So in this mode, tip is scanned in the contact with the sample, and then you have that feedback loop that maintains a constant cantilever deflection. So this part is the constant here. For example, here you can see the phase shift difference over the soft region, and I would like to talk more about this part. So this is how these images look like. These are elasticity images, and they show that each of the bumps in the soft material is basically shown here in the elasticity picture. And coming back to the phase imaging that I started to talk about. So what is it doing? So the phase imaging monitors the kind of phase lag between the signal that drives the cantilever to oscillate and the cantilever oscillation output signal. So in a tapping mode AFM, the cantilever is excited into resonance oscillation with a piezoelectric driver, for example. And phase imaging is used to map these variations in surface properties, as I've already mentioned. So what I want you to look at is that in a tapping mode, the feedback signal to the controller in the oscillation amplitude of the tip. And in simplified way to think about this is that the tip approaches like a raised part or like a bump in the sample, and it has less room to oscillate, and the amplitude increases. In response to the change of the amplitude, the controller moves up. The controller moves this tip upwards, so the amplitude goes back to the set point. So along with the amplitude, the frequency of the signal is also changing. And And here on the right hand side, you can see phase image, and regions with different mechanical properties are distinguished by these contrast of the phase, and it has quite high lateral resolution. So the topography image and the phase image, they are both generated at the same time. And usually when you look at these both images side by side, you can see the information that might be hidden from just the topography image alone. And the phase shift will also depend on the contact area between the tip and the sample. And for example, if the sample is perfectly flat and uniform, you will not see much change in the phase. But the phase will be slightly different along the edges of the features because of the slope, for example. And where you can apply this phase imaging. For example, you can identify the contamination. You can map different components in the composite materials. So this is composite material, different components. Then also you can differentiate regions of high and low surface and adhesion or hardness. You can also map different electrical and magnetic properties with different implications in the data storage and semiconductor industries, for example. In many cases, phase imaging will complement lateral force microscopy and force modulation microscopy, and will provide some additional information. And it usually gives you information faster and with a bit higher resolution. So this is it for today. This is the list of the literature that you can read regarding the information that we discussed today.
С вами был Тибериус. Если видео понравилось, ставьте лайк. Если видео не понравилось, так уж и быть, ставьте дизлайк. Но обязательно напишите почему. Подписывайтесь на канал. Всем пока. До скорого.